All right, so we have done the basics on the simplex method. We're going to be asking these questions today, so that's today's agenda. As you recall, in the graphical solution, we were able to tell whether we have a unique solution, we have infinitely many alternate optimum solutions. So if I have more than one solution, I have infinitely many solutions, right? Because you take any two, you take their convex combination, it's also going to be a solution. So either you have one solution of an LP, one optimal solution of an LP, or infinitely many optimal solutions, or no solution at all. It could be an unbounded case. So how do we figure this out? Using the simplex method. All right, that's the agenda. We're going to be talking about something called degeneracy, which is the only little problem with the simplex method. So as we discussed last time, simplex is probably the fastest that you can think of as an algorithm, right? You start at a point, you go to a neighbor, which is better, you go to a neighbor, which is better. So it's this greedy logic, and it's the simplest that you can think of, it's the fastest that you can think of, but because of degeneracy, it does not always act as this best possible algorithm. We'll talk about what slows it down. And then we're going to talk about BGAM and two-phase methods, which tell us how to figure out a starting basic feasible solution if we don't already have a ready-made one. So in the last two lectures, we were able to start with a basic feasible solution right away because I gave you a system in which I had all less than or equal to constraints. So if this is the case, and the right-hand side is a non-negative vector, the B vector is a non-negative vector, then you have the origin, or x equals to 0, feasible solution to this system, right? So when we change this to standard form by adding slack variables and making this equation, I can forget about my original variables, think about them as non-basic variables, take the slack variables as my basic set. It's going to be a proper starting basic feasible solution. So this is the case in which my system that I give you was all less than or equal to, and the right-hand side was a non-negative vector. A starting basic feasible solution was already available, and that was all the examples that we discussed last time. So BGAM and two-phase method will tell us what if that's not the case. Because we can have LPs which are not feasible, right? In the beginning, like in the graphical method, if the region is empty, that's an LP which has no feasible region. So we should be able to detect that as well. So that's two-phase and BGAM methods. All right? Let's talk about the simple one, the simplex for minimization problems. And how do we solve minimization? So for a maximization problem, what did we say? I'm going to have the rho 0 format. I'm going to write my rho objective function as z is equal to cx. Instead of that, use rho 0 format, z minus cx equals to 0. Always enter the variable with the most negative element in rho 0, and do your ratio test and so on. So you can switch that, change the most negative to the most positive. That's one way of handling minimization problems. Or if you just want to remember everything in terms of a maximization problem, you can translate your minimization problem to a maximization problem. That's even easier. So that's alternative number one. Instead of thinking a minimization function, think about the negated form and maximization of the negated form. So min f of x is the same as maximization of the negated form. So these two problems are equivalent. I just have to remember that in the end, I will take the objective function value, the optimal objective function value, and negate it to get to the optimal objective function value of the minimization problem. Does it make sense? So if you just want to remember everything in terms of the maximization, think about that LP on the left-hand side as a minimization problem, change it, negate the objective function, and remember to negate the actual value of the optimal solution to get to the optimal solution of the minimization problem. That's alternative number one. It's one of your options. And do not forget to negate is the keyword here. The other one is the direct way. So in row of 0 format, I have my z equals to cx, right? In row of 0 format, I say z minus cx equals to 0. For max, we have most negative entering. For min, this time you have most positive as the entering variable. That's the only thing which is different. And that's the same idea, right? Instead of cx, basically I am maximizing minus cx. So those two are two equivalent statements. Okay, so that's that. We don't need an example for that. Let's look at alternate optimal solutions. So when we detect alternate optimal solutions in the graphical method, you had an improving direction. The improving direction had isoprofit lines that were in parallel with one of your lines of the feasible region. So what the last point of touch is actually a set of points on the whole line segment. It's not a unique point, but it's a whole set of points. Okay, how do we detect this using the graphical method? The gentlemen, I'm not coming down this time, so they're sitting as far behind as possible. Okay, all right, so here's an example. We put a wording to it so that it makes more sense. It's a very simple example. So we have a company, it's producing 3 types of products: desks, tables, and chairs. We have 3 types of resources: lumber, finishing hours, and carpentry hours. So these resources are used in order to produce the products. And in these values, so in order to produce 1 unit of desk, I need 8 feet of lumber, I need 4 hours of finishing time, and I need 2 hours of carpentry time. All right, these are my resources. These are my 3 products. If I sell these products, I sell them per unit for $60. This is for a desk, 30 for a table, and 20 for a chair, all right? These are my selling prices. What else? I can sell as much as I produce, except 5 tables can be sold at most, all right? So I cannot sell more than 5 tables. This is what I know. And the objective is to maximize the total revenue with respect to these selling prices. All right, that's a very simple example. I don't even dare to ask and insult you. The variables are going to be the number of units of each product. They're going to be integer in number, right? But we're going to forget about integrality for a sec. And we have 4 constraints. 3 of them are my resource constraints. The per unit resource that I use for each product totaled up should not exceed my available resource for that type. So I have a lumber constraint, finishing hours constraint, carpentry constraint, and I have the limitation on the table demand that I cannot exceed the 5 units. Sounds good? So typically, I would like to see integers. These are tables, desks, and chairs. But I am going to make an assumption that it's OK to produce 3.2 tables, and then I will round it up to the nearest integer possible. All right, so I'm going to solve it as if fractional values are available. OK, so what do? I solve it with Simplex. This is the form that I like. It's less than or equal to constraints. So I add a slack variable. Let's call it S1 for this one. Translate it into an equation. Add another one here, another one here, another one here. So I have 4 slack variables. And if you look, the right-hand side is a non-negative vector, right? So you can take x1, x2, and x3 all equal to 0. It will be a feasible solution. So I can start out with this ready-made basic feasible solution. Because I cheated again, I gave you an LP, which is in less than or equal to format, and finding a starting basic feasible solution is very easy. Make sense? So I have 4 constraints, and I have the objective function. So I have 5 constraints altogether. I need 5 basic variables. Z, of course, is the objective function variable, is always a basic variable. And then I have my 4 slack variables as my basic variables. Sounds good? Is it in proper form for simplex to be applied when I translate my objective to row 0 format? When you look at under your basic variables, what do you see? You see the columns of the identity, right? So you have a unique basic variable appearing only in a single equation, and you have one basic variable for every equation, and that's your requirement for the Tableau format or for the canonical format. Okay? So you don't see S1 in the objective function, you don't see any of the S's in the objective functions. You see only the non-basic variables, which are x1, x2, and x3. So you will be able to pinpoint directly how can you improve this current basic feasible solution? Where should you go next? Does it make sense? So in other words, I'm saying that we have basic variables. What are my basic variables? I have S1, S2, S3, and S4 as my basic variables because I have 4 constraints. Z is also a basic variable. That's always the case. I have my non-basic variable. These are x1, x2, x3. If I set all my non-basic variables equal to 0, I have a unique solution in terms of the basic variables, and that's simply the right-hand side values, right? 48, 28, and 5. That's a ready-made basic feasible solution, and I will always be able to get to this solution as long as my right-hand side vector is a non-negative vector, right? Now, none of these basic variables appear in my objective function. My objective function is only in terms of the non-basic variables. So what was the requirement? In simplex, where do I go next? I go to a next one, which is a neighbor, right? What does it mean it's a neighbor? It changes rows with one of my non-basic and basic variables. So I will pick one of these x1 and x2 or x3, and I will ask the question, which of these should I move from 0 to upwards? Okay, the other will stay the same. So I will be able, with this row 0 format, with this proper Tableau format, I will be able to dictate which non-basic variable, if it moves from 0 upwards, is going to change the objective function by how much. Make sense? So if you look at your objective function, you don't see it that well. If you look at your objective function, if you increase x1 per unit, 1 unit, your objective is going to improve. Think about it, the 60 on the right-hand side by 60. If you increase x2 by 1 unit, your objective is going to increase by 30. So you're greedy, you ask the most improvements, so you say that x1 is going to be my entering variable in this first tableau. Does it make sense? Of course, when x1 goes up, all the basic variables will change their values. But none of them appear in my objective function, so I can pinpoint the net effect of incrementing x1 in this Tableau format. And that's why we need the canonical form representation, the Tableau form, and so on. Sounds good? Okay, so we have, clear this up, we have x1 entering, and I do my ratio test to see which of the current basic variables is exchanging roles with my x1. So x1 is going to be basic now. It's going to move from 0 to something higher. I am trying to find out the highest possible, such that my current basic variables and all the other remaining variables stay non-negative while preserving the satisfaction of the constraints. Okay, so what was my ratio test? I look at the column of the entering variable. I take my right-hand side value and divide it by the coefficient of the entering variable. 48 divided by 8 because of this coefficient, 20 divided by 4 because of this coefficient, and 8 divided by 2. What about this one? 5 there is no coefficient. So you can assume this is an infinite ratio coming from here, saying that no matter how high x1 goes, it's not going to limit the non-negativity of the basic variable, which is S4 here. Does it make sense? Okay, so the bottleneck, the minimum is which one? This one. That's going to be your leaving variable. So you do your pivot on their intersection, which is x1 and S3. Sounds good? In the next iteration, x1 is your basic variable. It replaces S3, and you want x1 column and S3 column to exchange. So in the third equation, you want to see x1 rather than S3. Make sense? And that's what we have over here. I have x1 appearing, replacing in new row 3, the role of S1, and I do elementary row operations to get from one tableau to the next one. Okay, so you take your third row, let me erase again. You take your third row, you want this one to be 1, you want this coefficient to be 0, this one to be 0, this one to be 0, and you do elementary row operations to get to that. And that's exactly what you have when you get here. You divide, for example, row 3 by 2 to get to row 3 prime. After you get your 1 there, you apply, multiply with a proper multiple to zero out the 4 over here, and so on. All right, these are proper elementary row operations, and hopefully there is no problems in doing that, right? Wake up, you can speak. No problems in elementary row operations? Okay, I got there. So I keep going. What is this change of 240? Is that expected? It was 0 before, and I moved to 240. Is that unexpected? What is the actual change in the objective function? So I chose x1. Why? Because per unit, it told me that I can increase my objective by 60 units, right? So if x1 is 1, I have an improvement in my objective to 60. If it's 2, I have 120. What is the final value that I get for x1 from my ratio test? It's the minimum one, which turned out to be 4 as the result of the ratio test. So 4 times 60, 240 is how you get the change from 0 to 240 in your objective function. Sounds good? Okay, you ask the question now, is this tableau optimal? Can I improve it? And the only option that you have is, currently you have basic variables, non-basic variables. Choose a non-basic variable from 0 to something higher. Would this make your objective function happier? And is this the case? As long as I have negative coefficients in my objective function, I can improve it, right? So I do one more iteration, and so on. So I get to this final tableau, which is now optimal. Why? Because if you look at the coefficients of all the non-basic variables, they are positive. Put them on the right-hand side in regular form, they will be decreasing your objective function, so you don't want to enter any one of them. Does it make sense? So this is your optimal tableau. So all well and done. So when I look at my optimal solution, what do I see? I see that x1 is equal to 2, x2 equals to 0, x3 equals to 8, and I have my slack variables, but these are my original variables. So meaning that x2 was standing for the number of tables, I produce no tables. So in my optimal solution, it turned out that there are no tables in the production. And that's a unique solution, by the way, at this point. We're going to make it more favorable to produce tables. How do I make more favorable to produce tables? Instead of having this 30, if I make its contribution higher, it might be the case that tables will be more beneficial in the optimal solution. So right now, ignore the total product of tables. You don't lose anything in terms of your revenue, right? So what if I increase this number, and I'm going to increase this number to 35. Okay, instead of 30, I am going to change it to 35. Why 35? Let me convince you that 35 is enough. So instead of 30, I'm going to start and make this 35. What would change in terms of my steps, do you think? Again, the first entering variable is not going to change. Some numbers are going to change, but those numbers are only going to affect rho 0 and x2 coefficients. So this number is probably going to change, and this number is probably going to change. And what do you think this number would become? If I start instead of with 30, 35, what would happen to this plus 5 in the end, do you think? Guess. Don't have to do elementary row operations right away. 10 is a good choice. Go the other direction. You changed it by 5. Why? Because the change here was 30 to 35. 0 is going to be the difference. This was minus, this was plus, so think about it that way. So if you decrease it more, that means that you will have that plus 5 as plus 0 instead of plus 5. But you don't have to guess this. You can do the steps of the simplex method with 30 replaced with 35 over here. Do the exact same steps. Again, the most negative will enter, so x1 will enter. Again, I will do pivot operation in this first step on that element. I will get to the next one. x2 will enter, and again, the same variable will leave, and I will come to a point in which I have my final tableau. If you look, the number is again the same. Not the same, of course. It cannot be the same. No, it is the same. Why is it the same? Number is 280. It's the same. Why? Because we have an alternate solution, and x2 was equal to 0 in the original solution. So its coefficient had no effect in the 280, and I change it now, and I come to a solution in which constraint-wise, x1 and x3 values have to be changed and adapted, and I have the same resulting 280. Okay, so let's see why this is an alternate optimum solution. So this is my optimal tableau, right? 280, I have non-basic variables with positive coefficients, so that's my stopping criteria. No variable can enter and improve my objective function, okay? But how did we say this improvement from here to here was 0 to 240? How did we get there? We looked at the coefficient of the entering variable. We looked at the result of the ratio test. We multiplied, and that was a change in my objective function, right? 60 times 4. That's always the case. My entering variable coefficient tells me per unit how much improvement I expect in my objective function, right? And my ratio test tells me how much can I increase that value of the entering variable. So the total, the product, is going to be my net change in my objective function. So always keep that in mind. In other words, this is the formula I'm talking about. The net change in the objective function is the coefficient of the entering variable, and I put in absolute values because whether we're doing min or max, it doesn't matter. This is the net change in absolute value. You go for the favorable direction. Either you go up or you go down for minimization, times the result of the ratio test, okay? So if I have, for example, maximization problem and negative coefficient, I would still continue because that's a way of improving my objective function. But if, for example, the coefficient of the entering variable is 0, you have your optimal tableau like this one, and you have a non-basic variable with a coefficient which is going to be equal to 0, then the net change in the objective function is going to be 0, meaning that that's your Q for potential alternate optimal solutions. Does it make sense? So if this value is not a non-zero value, you always improve. But if it's a 0 value, you have the chance of getting the same objective function value. Okay, and that's going to be the case here. So I have S1, X3, X1, and S4 as my basic variables. So what are the non-basic ones? What are the ones that I have the option of moving from 0 to higher? There is the option of X2, right? That's non-basic. What else? S2 is also non-basic, and S3 is also non-basic. But S2 and S3 are going to worsen my objective. This is a negative value on the right-hand side. But X2, if it enters, it's going to have 0 change in my objective function. But perhaps I will have now some tables produced in my production. All right, so let's do a pivot, enter X2, and leave the minimum, which is X1. I get to a different solution, but if you see, there is no change in the objective functions. I have 280 before, and again, I will have 280 because the coefficient of the entering variable is 0. If it's 0, you expect no change in your objective function. Does it make sense? But as a vector, I have a different vector now. And in particular, I am producing some tables in this new solution. Right? So if we just look at our variables, original variables, I have in this solution, my variables are x1 equals to 2, x2 equals to 0, x3 equals to 8. That's one solution with value 280. And I have another solution here in which x1 this time is not produced, but I have x2, 1.6. Remember, non-integer values are allowed, and this has the same objective function value. Make sense? So we have alternate optimal solutions, and if I have any two solutions, so is their convex combination. Any convex combination of these 2 points is also going to be an optimal solution with the same 280 value. And this is the table which lists that. So you have two optimal solutions, as I stated on the right. So you take your lambda value, any multiplier for convex combination, you multiply the first one with lambda, the second one with 1 minus lambda, you get to a convex combination on the line segment between these 2 points. So you have x1 and x2, you have the line segment, all of these are your optimal solutions. Like your graphical solution, you have 2 corner points, and everything in between is also an optimal solution. Sounds good? Any questions on this? Okay, so tons of course, there are some, only a sample here, there are tons more. So what have we learned now? When do I know there are alternate optimum solutions? I look at my optimal tableau. First of all, I have to have an optimal solution to be able to talk about alternate optimum solutions, right? So I get to a tableau in which I have optimum solution already, and then I look whether there exists a non-basic variable with 0 coefficient. That's a potential alternate optimum solution, just like in our case. In my optimal tableau, I had x2, which was non-basic, with a coefficient equal to 0. That led to an alternate solution in which x2 has a positive value as this vector, okay? But that's not a guarantee. So in order for me to have alternate optimum solutions, one requirement is that I have a non-basic variable in the optimal tableau with 0 coefficient. That's not enough. I still have another requirement, and the requirement is that when that variable enters, I want a change in my vector, okay? So the result of the ratio test also has to be a non-zero number. Does it make sense? Why do we need that? So, okay, what is happening in Simplex? You choose your entering variable, right? That has some value coming from the ratio test. In the next iteration, the entering variable moves from 0 to the value of the ratio test, right? Now, if the value of the ratio test is also 0, you had the non-basic variable entering, hopefully, to be going up from 0, but the ratio test tells you that it can only stay at 0. So it enters at 0, but it goes up until 0, meaning that the vector is not changed. So in order for me to get to alternate optimum solutions, not only do I need a 0 in the coefficient of the entering variable, but I need the result of the ratio test to be non-zero, so that when it enters, just like in the table's case, it goes up from 0 to something higher. Sounds good? Does it make sense why we need that? So that's why over here, even if there is a non-basic variable with a 0 coefficient, this is not always guaranteed to be alternate optimum solutions. It is possible that I still have a unique solution. I need, so the extra requirement here is that I need ratio test result to be non-zero. Okay, we'll talk about when the ratio test result can be 0, and this is a problem which we call degeneracy in just a second. Does it make sense? Cool? Good. Okay, let's do this practice together. So this is an example which you can look and see directly. You can jot down the graphical solution and see that there would exist actually alternate optimum solutions. Okay, but let's see whether we can do this with Simplex. So if I draw the region, what will I get? I will have 5 and 5. So I will have one of the lines going through that's one of the lines, and I have to stay below, right? That's my x1. This is my x2. It's not really a big deal to draw this. And then I drove it, the second one, like this. That's my feasible region. And if you look at your objective function, it's actually parallel to your first constraint, right? And the improving direction is going to be actually this normal. So you'll have that set of alternate optimum solutions. Okay, so in the graphical solution, you know this. You know that you should expect this point A as well as this point B, as well as any convex combination, the whole line segment to be the set of optimal solutions, right? Okay, let's see if we can detect this using the Simplex method. So how should the Simplex start? I need the standard form. So I have z minus 2x1 minus 4x2 equals to 0. This is canonical form. And I need equations instead of less than or equal to constraints, right? So I add slacks. x1 plus 2x2 plus s1 equals to 5. x1 plus x2 plus s2 equals to 4. All right, now everything is in standard form. I have non-negativity of my variables, right? I can initiate Simplex without a problem. Make sense? Okay, so I need another page. Let me draw the tableau here. In tableau form, I have variables x1, x2. I added s1, s2. I have my right-hand side. And I have my coefficients in row 0 format of z, 0 right-hand side. I have 1, 2, 1, 0, 1, 1, 0, 1, 5, and 4. And that's my S1, and this is my S2. Okay, so I embedded my standard form into the Tableau form. Sounds good? So where am I on the left-hand side in this graph at the starting basic feasible solution? I am at this origin corner point, right? X1 and X2 are my non-basic variables. S1 and S2 are my basic variables. And I have S1 and S2 with non-negative values. And X1 and X2 have values 0 and 0, right? That's my starting basic feasible solution. I need two basic variables. That's my S1 and S2 for the first two equations. And the remaining variables are my non-basic variables. So for example, if you look at and eliminate the first two columns in your Tableau, you will see exactly what is the current solution. It has value equal to 0, exactly because you're at the origin. Your S1 is equal to 5, and your S2 equals to 4. All right? You see the solution right away. That's why you need the canonical form representation to have this. Make sense? Okay. Now in Simplex, because this is a maximization problem, I will ask to improve the objective by moving to a neighbor by changing one of the current non-basic variables from 0 to something higher. Which one you would choose? You would choose X2 as your entering variable because it has -4 rather than -2, higher potential of improving, right? And then I will do my ratio test. What does the ratio test tell me? How much can I increase this X2 without hurting the feasibility of the others, without leaving the feasible region, in other words? So I am here. I am basically asking to move along this direction, right? Move X2 to something higher. What is the highest possible value? You can't go higher than 5/2. You see it on the graph. What about the ratio test? So in my ratio test, I have X1. That's my first equation. This is my first equation, right? X2 is going to go up. X1 is going, X2 is going to go up, but X1 is going to stay at 0, right? So I have S2 equals to 5 minus 2x2. I want this to be non-negative, so I say that x2 cannot be more than 5/2. That's my ratio test. And the simple form was to look at the right-hand side, look at the coefficient of the entering variable, and take the ratio. That's why the name ratio test is coming. Make sense? So that tells me x2 cannot exceed 5/2. From here, I have another bound, which is 4/1. But because 5/2 is more limiting, I have my pivot operation as x2 entering and s1 leaving my Tableau, right? So I need to do a pivot operation on this element over here, exchanging the roles of x2 and s1. Does it make sense? So let's do that. Oops, I don't want that. So let's do our pivots. So instead of S1, I will now have X2. S2 is going to remain as is. Instead of 2, what do I want? And this number, I want X2 column to look exactly like S1 column. So I need this 2 to become 1, right? So how do I do it? With elementary row operations, divide through with 2. So I get 1/2 from here. I get 1, 1/2, 0, 5/2. And that's exactly what I expect, right? That's the new value of x2 in the new solution, and I have moved from this corner point to that corner point, so 5/2 for x2 is expected, right? Okay, what about this number? I don't like the 1, I need to change it to 0, right? Just like this column. So how do I change that to 0? Now that I have the 1, multiply this row with -1 and add it to this row to get your 0. Does it make sense? So now that you get the 1, you can use this 1 to get to this 1, 0, 0 form very easily. I'm sorry, this is not, you're not helping me here. That should be S1. This should be S2, and I'm actually replacing with this column, not that one, right? I shouldn't dare erase it. Does it make sense? So x2 is going to exchange rows with S1. So the column that it will replace, these two columns are going to exchange rows, not the S2 column, I'm sorry. So I want to see the 1 here, I want to see the 0, 0 exactly on the left-hand side. Okay? So let's go back to where? To the very beginning. More. Okay. So that's my pivot element. And I want to see, this is my S1, this is my S2, that's my problem there. I want to see X2 column just like the S1 column. So I want to see 1 here, 0 here, and 0 there. Okay? The 1 is very easy. Divide through with 2. Let's do that. So I get X2 here, 1/2, 1. 1/2, 0, 5/2, that's expected. That's my new value of x2. To get the 0, how do I get the 0? I multiply this last row that I got with -1 and add it to that row. Okay, so if I do that, I have -1/2 plus 1, I will get 1/2 here. -1 plus 1, I will get 0. -1/2, right? -0 plus 1, 1. -5/2 plus 8/2. I should have 3/2. Does it make sense? And somebody should correct me on this. So S2 is still the basic one. It hasn't changed. And what about my objective? So in order to zero this out, now that I have my 1 here, I can multiply this row with, let's do it with another color, with 4 and add it to the objective row. Okay? So if we do that, what will I have? I will have 4 times 1/2, which is 2, added to -2, I will have the 0 here. 4 added to -4, I will have the 0 here. 4/2 plus 2, I will have 2, 0, and I will have 10 here. Okay? Does it make sense? So am I indeed at this point? Exactly, this is x1, 0, x2 equals to 5/2. And if you plug in the values in these equations for the standard form, you get the S1 and S2 values uniquely. You see that x2 is 5/2. You see that x1 does not appear as a basic variable, so it should have value equal to 0. So x1 should be equal to 0. Does it make sense? Now, is this optimal? Yes, right? Yes. What did I do in the row of the 10? Okay, what is my aim? Remember, I want to change this x2 column, right? Look at the x2 column. x2 is going to replace x1, right? So x2 column should look like s1 column. So in other words, I want that -4 to be 0. So how do I get the 0? After I get my 1 here, right? If I multiply this with 4 and add it to the objective one, I will get the 0, right? So did we do it wrong? I multiply this with 4, 4 over 2, add it to -2, I get the 0, right? I multiply this with 4, add it to -4, I get 0. 4 over 2, add it to 0. So 2 plus 0, I get the 2. 4 times 0, add it to 0, I get 0. This is 4 times 5 over 2, 20 over 2, added to 0, I get the 10. Is that good? And you should check it, this 0, how much improvement do you expect? The coefficient of the entering variable, which is 4, times the result of the ratio test, which is 5 over 2, and that's 10, should be expected. All right? So this is your new tableau, and it should tell you exactly that you are at this point rather than at this point now. Okay, but now this is optimal. Why is it optimal? Because I don't have any negative coefficients in my objective. What are my non-basic variables? x1 is non-basic, x2 is basic, x1 is non-basic, and s2 is basic. So I have 2 non-basic variables, 2 basic variables. But if you look, this is a hint of alternate optimum solutions. You have a non-basic variable with a potential 0 coefficient in row 0. And if you go back to here, that's where we are, right? There is the potential of alternate optimum solutions because there is a non-basic variable with 0 coefficient in the final tableau. Okay? So again, this is the condition. So one prerequisite is satisfied. I need to guarantee that if I enter that variable, I will have a ratio test which is different from 0, and I will move to a different vector to get an alternate optimum solution. Does it make sense? So we are here. We have the potential because there is the 0. But the question is, if it enters, will it change my objective function? It won't change my objective function. I know that I will stay at 0 because the effect is going to be 0. But will I get to a different vector than my corner point over here? Okay, will I? So you will do another ratio test. You will do another pivot operation, right? Let me do it. Where should I do it? Let's do it here. So I have 0, 0, 2, 0, and 10. I have 1/2, 1, 1/2, 0, 5/2. Let's finish this and then take the break. Okay, so that's Z, x1, x2, s1, and s2 on right-hand side. Okay, so I have a potential non-basic variable, which is x1 that can enter. I do my ratio test. I take 5/2 divided by 1/2. That's the ratio of 5. I take 3/2 divided by 1/2. That's another ratio of 3. This is the minimum one, so that's going to leave. All right, so if I do a pivot operation in which x1 becomes a basic variable with positive value, and the positive value is equal to 3 here, I will get to a different vector, which is going to be also an optimal solution. Okay, I am not going to do the steps here, but let's see what will happen. So instead of x2 and s2, that was the case before, I will have x2 and x1, right? 10 is not going to change. That's going to be still the right-hand side value. The x1 is going to be equal to how much? What will be this number, you think? How much? x1 was currently at 0. It entered. Non-basic variable moved from 0 to something higher. What is the highest value? That's the result of the ratio test. So I expect I expect that 0 to be equal to 3 in the next iteration. Does it make sense? If you do elementary row operations, of course, make this 1, 0, and 0, you will get to the same number. But we can guess it also directly, so that will be 3. If x1 is equal to 3, what will be the value of x2, you think? X1 equals to 3, what will be the value of, it's going to be equal to 1, right? So this value should be equal to 1. So do the elementary row operations, fill in the gap, you get to a different solution, and that different solution is exactly this vector B over here, which is 3, 1, I think. Okay, so A was my one optimal point that I find on this tableau. I get to B if I enter my x1 variable, which was non-basic, at 0 coefficient in row 0. I get to a different vector, and now everything in between is also going to be a set of optimal solutions. Does it make sense? So please carry out the steps thoroughly. And you will see that this is one vector, that's your A vector, this is your B vector. When you append S1 and S2 as well in the standard form, and any convex combination for any lambda in this range is going to be an optimal solution as well. You put lambda equals to 1, you get this A corner point. You put lambda equals to 0, you get B corner point. But of course, any value of lambda is going to get you to a new optimal solution. And all of them will have value equal to 10. Okay, you should plug in and see that that's indeed the case. Sounds good? Okay, let's take a break now.